Hello, today in our lecture we are going to discuss one of the most important topic called growth of functions. Here we analyze the functions in terms of some well-known notations called asymptotic notations. In computer science, to solve any problem, we write a program using any programming language like C, C++, Java, etc. But before writing any program, we generally write an algorithm. So the steps we can think like if we have a problem to solve, then from that problem we are trying to design an algorithm or set of algorithms, and from that algorithm we write and program to solve the problem. So in this design and analysis of algorithm, the design means how to design different algorithms to solve a problem. For example, if we have a problem, we may have different algorithms to solve the problem. And our analysis part, what we do actually, we compare all these algorithms, algorithm 1, 2, 3, 4, and mainly in terms of time and space, that is which algorithm is taking lesser amount of time and which algorithm is taking lesser amount of space. In terms of this time and space, we try to analyze all this algorithm and find out which one is the best. Then we write the code using any programming language to solve the problem. So this is the approach. First of all, we try to design the algorithm. The algorithm may be different algorithm to solve a problem. Then we analyze the algorithm, which algorithm is better or best to solve the problem. Then we select the algorithm and write the program to solve the problem. Now, in algorithm, different notations are used to analyze the algorithm. These are called asymptotic notations. We have three well-known notations. First one is called big O notation, then big omega notation, and big theta notations. We'll learn one by one all these three notations. Let us consider we have an algorithm A, and we are going to plot the running time of the algorithm A in this graph. In the x coordinate, we consider the number of input, and in the y direction, we consider the time taken by the algorithm to execute. And if we plot the graph like this, where as the input size increases, with that if the running time also increases like this, and this is, we can say, the time complexity or the rate of growth of time as we increase the number of input. And if we call this function as fn, fn is the running time of the algorithm A, and this is the plot of the fn as the number of input increases. Now, if we can find out another function called cgn, where c is a constant, and this function cgn is always above the function fn after a certain point n0, that is, if fn is less than equal to c of gn for all n greater than equal to n0 and for a c not equal to 0. That is, after finding out fn, if we could find out another function gn for which after a certain time or after a certain number of input n0, the function c into gn is always greater than the fn, then we can say gn is the upper bound of the function fn, and we could write fn is equal to order of gn. Big O is for the upper bound of the running time fn of an algorithm A. Now let us consider an example. Consider fn is equal to 3n plus 2, and let's say gn is equal to n. Now can we say fn is equal to order of gn? Let's check. To hold this equation, this inequality should satisfy. Fn is equal to 3n plus 2 should be less than equal to some c into n. So we have to find out a constant c, and also we have to find out a value of n0, and which should be greater than equal to 1. From this inequality we can say C is equal to 4. That is 3n plus 2 is less than equal to 4n. We can also find out the value of n if we transfer this n into left side. From that we can find out n0 is equal to 2. So this inequality holds, n0 is equal to 2 and c is equal to 4. So we can write Fn is equal to order of Gn is equal to order of n. And actually this is true for Fn is equal to order of n square. Also it is order of nq. It is true for all the higher order of n. But we will only take the tighter one, or we will go for the least upper bound. And the general approach is, if Fn is equal to a1 n to the power 3 plus a2 n to the n square plus a3n plus a4, in that case we'll only consider the higher order term. So Fn always will be upper bounded by n cube. So this is the general rule. If the running time has the equation like this, and it will be upper bounded by the higher order term, we can leave all the lower order terms. Next we will discuss omega notation.